In this video, I want to talk to you about the relationship between electrons and emission spectra. Now, we've been talking about Bohr's model of the atom, how electrons are arranged around a nucleus. And he places the electrons in energy levels or energy shells moving out from the nucleus, distinct places, almost like orbits around a sun in a solar system. This model, he developed it by studying light that was given off by energized electrons, or electrons that had energy added to them. And so I want to explain a little bit what he discovered and how that helped him come up with this particular model. But first we need to start with light. What exactly is light? Well, it is known as electromagnetic radiation. It's a type of energy that has wave-like behavior. It behaves like a wave as it travels through space. Of course, light can go through the vacuum of space. It doesn't need matter to carry it along. All types of light have a particular speed, 300 million meters per second. Light can have a variety of wavelengths. They can range from as long as 100 kilometers per wavelength. And if you draw a wave, it kind of goes up and down like this. So a wavelength would be from the crest of one wave to the crest of the other. So wavelengths of light can be very long, or they can be very short, 10 to the negative 18 meters. So that's a decimal point, 17 zeros, and then a 1 of a meter. Wavelengths, or another property of light is frequency, which is related to wavelength. And frequency is a measure of how many cycles, how many wavelengths happen in a second. We measure that in a unit called hertz. Electromagnetic radiation, or EM radiation, also can act like a particle, so not only like a wave, but also like a package of something, a little piece of something. And we call those packages of light photons. Electromagnetic radiation is caused by moving charged particles. It happens naturally in places like stars, but of course we also can create it. So the wavelength and frequency of light determines how that light interacts with various substances. For example, very long radio waves will interact with radio receivers, but they don't interact with living things. We have radio waves traveling through the air all around us, and we are not affected. Microwaves of various sizes are used for things like cooking our food and talking on our cell phones. So again, the size of the wavelength or the frequency, that they're very closely related, that will determine how that light interacts. The visible spectrum we are very familiar with. That's what people tend to think of when you say light, because it's visible light. And the different wavelengths and frequencies give us all these different colors. And then, of course, things like X-rays will interact with bone. They can be absorbed by calcium, and that's what gives us our X-ray imprint. And various dangerous gamma rays, or radiation, interacts in a negative way with our DNA and our cells. So one of the ways that light interacts with electrons is something called the photoelectric effect, that certain metals will actually spit out their electrons, eject their electrons, and as those electrons move, as those charges move, it creates an electric current. This process is part of what makes solar panels possible. Now, with the photoelectric effect, with this interaction, only certain frequencies of light will work. So not every light is going to cause an electric current to develop. And that was the research that helped develop this idea that light comes in photons. It comes in certain packages of energy. And when the right package of energy interacts with the metal, then you get the change in the electron. So while the photoelectric effect kind of got everything started in this understanding of the relationship of electrons and energy, it's the emission spectra that I want to focus on for the rest of this video. Electrons can absorb energy and not be moved, but in turn they give off light. It can be visible light, as we see down here in these various illustrations, or it could also be invisible light. So things glow in the dark because they have absorbed energy from the visible light, and then you turn off the lights, and that light is returned to you as the electrons give it off. You can also add heat energy to various ionic compounds, and the metals in those compounds will be giving off light. So we have examples of lithium, sodium, potassium, and copper here. You can also run electrical energy through a gas and create light. This is what powers our neon signs, or our, in a multi-step process, the fluorescent lights we have in the the ceiling of our classroom. So the color that you see when these electrons are excited, when you have emission happening, actually includes many different wavelengths. And so this green flame that we see for copper, if you take that and split it out, you can see there's a whole variety of wavelengths being shown here. It's from the very dark purple on one end to our red on the other. There's a piece of equipment called a spectrometer, which uses a diffraction grating, which is kind of like a very sophisticated prism, to separate the light into all these different wavelengths. And every atom has its own unique emission spectra, where that atom will only give off these particular wavelengths when those electrons have been energized. And this can be used actually as a forensic technique, a way to determine the composition of substances by energizing that substance and looking at what pattern of wavelengths are given off, what the emission spectra is for that particular element. For example, if you're only seeing these 3 lines of purple, teal colored, and red, then that's an indication that hydrogen is present, whereas many more lines you can see are possible with iron. In general, the more electrons that are present in an element, and iron, of course, is much bigger. It has many more protons and many more electrons than hydrogen, with its 1 proton and 1 electron. And so the more electrons that are available in an atom, the more complex the emission spectra will be. So Bohr used the emission spectra of hydrogen, where we saw just those 3 lines, to help develop his model, this idea that electrons move between distinct energy levels, that they can't exist anywhere around the nucleus, but they have a particular place that they belong based on how much energy they are carrying. He discovered that electrons, or proposed that electrons exist only in those energy levels. They never exist in between. So it's kind of like going up a set of stairs or a ladder. You land on the rungs, but you can't kind of hover in between. You are either on this step or on that step. The process is that electrons seem to absorb energy and once they do, they can jump to a higher level. So they kind of suck it in and then move to a higher level. But then electrons don't stay there. They don't stay in that excited state. They want to return to their lower level, which is known as the ground state. And when they do that, they release that energy. The energy going in can be of a variety of types. In a previous slide, I talked about heat energy and electrical energy. And that energy, once it's released, doesn't have to come back out as heat or electrical. It's released back out as light energy or as photons. And depending on the wavelength, you get a particular color. So this model tries to show that you've got absorption of energy coming in, a photon, in this case, a package of energy. This electron, this little yellow circle here, will absorb that energy, suck it in, and it can't exist in this lower energy level anymore once it's high powered. It has to go faster, so it jumps up to a higher energy level. But that's not its natural state, and so it's not going to stay there, and so it will get rid of that energy. It will emit it, and it emits it again as light energy, and so this we would see as a visible color of wavelength, and then the electron would return to that lower energy level until more energy comes in. So Bohr's model is not, of course, the final model. It's not exactly how we understand atoms today. Other scientists after him discovered that electrons can move in seemingly sub-levels within an energy level, and they also move in a random pattern, not a circular path that looks like a solar system. So because of that, our modern drawings of the atoms usually show electrons in a cloud, as we see over here in a picture, which is really a probability. Where are we more likely to see an electron if we were looking for it? And those electrons in this case would be found in this darker area we see around the nucleus. That's the more likely place to find the electron, but occasionally they're out in this larger space as well. And so our modern understanding doesn't look quite as neat and tidy as Bohr's model, and we tend to just keep Bohr's model when we're doing introductory chemistry. But if you were to go on and study at a higher level, you'd be thinking about electrons in clouds. So emission spectra helped us understand that electrons have distinct places that they exist outside the nucleus, and that energy can be absorbed by electrons and then released as certain wavelengths of light.